Okay, this is chapter 7, Newton's third law. Let's consider that you push hard on the corner of a table with your finger. You create a force, or you generate a force on the table, and the table also produces a force on you. This is seen by the fact that when you push hard, or when you push on the corner of the table, your finger depresses, or your finger has a dent in it. The dent becomes deeper as you push harder. This tells us that forces are interactions between two objects, or interactions between objects. So let's suppose that we have two objects labeled object 1 and object 2. We can say that if these two objects interact, then the force that object 1 exerts on object 2 is F12, and in return, object 2 exerts a force on object 1 given by F21. By Newton's third law, these forces are equal in magnitude but act in opposite directions. We can write this symbolically as force F12 is equal to minus force F21. Note that forces are vectors, so I put a vector notation on it. This is basically Newton's third law, and we shall look at how this applies to various situations next. Let's look first at an object falling close to the surface of the earth. So this is in section 7.2, analyzing interacting objects. First of all, objects falling close to earth. So what we have is an object like that. Let's say it has a mass lowercase m, and it's falling close to the surface of the earth. So let's draw the earth like a ball, like that. And let's say the earth has uppercase mass m, and then we can now identify the forces on each of these objects. So this object will have a force acting this way, and the opposite of that, or the action of that is, so let's call this force F action, and this is F reaction. So we can say that in identifying forces on objects, we can call one force the action and the other force the reaction. So F subscript A is our action force, and F subscript R is the reaction. Now it doesn't matter which force you call an action force and which you call a reaction force, so it's purely arbitrary. You can call one force action and the other reaction, or you can switch them. It doesn't really make any difference. So once we identify the forces acting on each of these objects, we can then apply Newton's second law to see what happens to their accelerations. So we start off by, we next isolate each object by itself and apply Newton's second law. So we take the first object, the smaller object falling close to the earth. It has a mass lowercase m, and it has a force F subscript A as it falls close to the earth. By second law, that is by Newton's second law, the net force on this object is the force F subscript A. That is the only force present, and this should be equal to the mass of this object multiplied by its acceleration. Okay, so from that we can calculate the acceleration of this object A. We can calculate the acceleration due to the action force as shown. That acceleration is then equal to the force F subscript A over the mass. We next look at the larger mass, which is the earth. So this is the larger mass. So we've already drawn the earth this way. We said the force acting on it is going to be pointing that way. It's the opposite. It's the reaction force to the action force of the falling object. So this object is the earth has a large mass m, uppercase M. So this is the reaction force. And we say that by second law, the net force acting on this object we know is equal to the mass times acceleration. The net force present is just the reaction force, and that is equal to the mass of the earth multiplied by the acceleration of the earth. And this acceleration can be written as the reaction force divided by the mass of the earth. Let's look next at another scenario, an object sitting on the surface of the earth. So this time we draw the earth again. This time let's draw the earth. Well, actually I'll draw it again the way I've been drawing it, just as a semicircle like that. And then I have a box sitting on the surface of the earth this way. And so with this box sitting on the surface of the earth, the box is going to pull on the earth with a force. Let's call it F. F subscript R, and the earth pulls on the box with a force. Let's call it F subscript A. So we are just labeling one force an action force and the other force a reaction force. And then the interaction between the surfaces gives us the support force. So this is a force due to the earth pushing up on the object, the force of earth on object. And then this is the force of object on the earth. So the force A is the action force due to object pulling on earth. Fr is the reaction force due to earth pulling on object. And then FEO is the force of the earth on object at surface. We can think of this as an action force if you want. Let's call it an action. And then the force of object on the earth is the force of object pushing on earth at surface. And this is a reaction if you like. And so we can now isolate each object individually and then apply Newton's second law to each object. So let's do that next. So let's take the small object sitting on the surface of the earth. So that object is here. Let's say that object has a mass lowercase m, and it has this force, which is the force of the earth pulling on the object. So this force is the weight of the object, so it's the action force. We typically know this force as the weight of the object. And the other force acting on the object is the support force, which is the force of the earth on the object. So F subscript A is the weight of the object, or we can say it's known as the weight of the object, and Fe subscript O is known as the support force, or in some books it's called a normal force. By applying second law, we have the following. Net force, of course, is equal to the mass times acceleration of the object. Since the object is not moving, acceleration is equal to 0. So the net force on it are the external forces. We can say that FEO minus F subscript A are the net forces, and those forces should be equal to 0. Therefore, the FEO is equal to F subscript A, which we can interpret to mean that the support force or normal force is equal to the weight mg. So let me put mg here for weight, and normal force here, let's call it F subscript n. So the normal force is equal to the weight. This is typically what we know for an object sitting on the surface. Let's look next at the earth. So again, the same scenario applies. So we have a force like this, which is a force of object on earth. And then we also have this force, which is the reaction force due to the object pulling on the earth. So by isolating the earth by itself, we can see that the net forces or the external forces are FEO and FR. So the same rule applies. By second law, the net force is equal to the mass, which is the mass of the earth, times acceleration. And since A is equal to 0, we have the following, that the force of object on earth is equal to the force of the reaction, or the reaction force. Let's look at another scenario where we have a person walking on the earth. So we draw the earth again, and we draw a person walking on the earth, like that. So let's consider just the forces acting between the person's feet and the earth. We shall ignore the weight of this. We shall ignore the weight. So in this case here, we can see that as the person is walking on the earth, the person pushes on the earth with a force which we shall call the action force, and in reaction to that, the earth pushes on the person with a force which we shall call the reaction force. This person has a mass lowercase m, and the earth has a mass uppercase m. So we've identified the action and reaction forces on this system of the earth and the person by using Newton's third law. Now let's isolate each object individually and analyze. Consider first the person. So we have this person walking on the surface of the earth, and so the external force acting on this person is the force given here, which is the reaction force of the earth pushing on the person. So by Newton's second law, the net force on this person is just equal to the mass of the person multiplied by their acceleration. And so since the net force is just the reaction force, F subscript R, we can say that's equal to M times A. Therefore, the acceleration of this person will be given by the reaction force on them divided by their mass. Note that the reaction force, F subscript R, depends on the frictional forces. So frictional forces between the person's feet and the earth surface. Now let's analyze the motion of the earth, or let's consider the earth next. So we have the earth again, and this time the force on the earth is the action force due to the person walking on the earth. That force acts in the opposite direction and acts on the earth. By Newton's second law, the net force on the earth is equal to the mass of the earth times acceleration of the earth. And the net external force on the earth is just the action force due to the person walking on the earth. Therefore, we can say that the action force is just equal to the mass of the earth times the acceleration of the earth. Okay. Let's use A subscript E for acceleration of the earth, so that we separate that from the acceleration of the person. So we can say that the acceleration of the earth is equal to the force, which is the action force, divided by the mass of the earth. We will also note that F subscript A is equal to minus F subscript R, as we already know from Newton's third law. So if you like, we can say A subscript E, which is acceleration of the earth, is equal to the force F subscript R divided by the mass of the earth. And if we can put a negative force here, which tells us that the acceleration of the earth is going to be opposite to the direction in which the person accelerates. Let's try a quick example to illustrate this point. Suppose a 75 kilogram person exerts a force of 100 newtons on the earth as they walk. What is the acceleration of the person and the earth, and the acceleration of the earth? So we can draw this scenario again and say that this is a person walking on the earth, and this person applies a certain force to the earth as they walk. They said this force is equal to 100 newtons. So this force was our action force. So we say this is the action force, and this is a reaction force. And we said the action force, which is the force the person exerts on the earth as they walk, is 100 newtons. Okay, the mass of the person is equal to 75 kilograms. Mass of the earth is 6 times 10 to the power 24 kilograms. And we want to find the acceleration of the earth and the acceleration of the person. So just using the formulas we developed above, the acceleration of the person is equal to the force due to the person, or the force F subscript R over the mass of the person. We know from third law that the force A is equal to minus the force P. So the force on the action force is equal to the reaction force that acts in an opposite direction. Okay, let me put the signs correctly so that it doesn't confuse you. I guess we can use that. That will be fine. Or if you like, we can use FR equals minus FA, just to follow the conventions that we've adopted. So our convention is that forces to the right are positive and forces to the left are negative. So notice that FA is equal to minus FR. So we are following the convention that the forces to the right are positive and the forces to the left are negative. Okay. So now we can find the acceleration of the person, and this will be equal to 100 newtons divided by 75 kilograms. And that should give us the acceleration of the person. So this is 1.33 meters per second squared. And then the acceleration of the Earth should be equal to the force of 100 newtons, negative 100, divided by 6 times 10 to the power 24 kilograms. And this gives us 16.67 times 10 to the power negative 24 kilograms. Of course, it's negative, and you can write it as 1.667, negative 1.667 times 10 to the power negative 23 kilograms. So you can see that the acceleration of the Earth is very tiny compared to the acceleration of the person. This is why when you're walking on the Earth, you don't notice the Earth rolling underneath you. But if you were on a log that was in water, as you try to walk on the log will roll the opposite way, which tells you that this notion of accelerations that we've calculated is entirely correct. Let's look next at the example of the mule and the cat. So let's consider a mule. Let me see if I can draw a mule. I'll draw a mule with blocks like that. And the mule is connected by a string to a cat. This is the cat, and this is the wheel of the cat, like that. So the mule is walking on the surface of the Earth. So this is Earth, this is cat, and this is mule. So as the mule is walking, the Earth pushes on the mule. So this is the force of the Earth on the mule. In return, of course, the mule pushes on the Earth. So this is the force of the mule on the Earth. And then as the mule pulls the cat, this is the force of mule on cat. And by Newton's third law, this is the force of the cat on the mule. So I've identified the various forces. We are going to ignore the force between the wheels and the Earth. So I'll just write here, we are ignoring the force between wheels and Earth. Let's now analyze each object individually. Okay, so we start off with the mule. Actually, let's do this. We will put the mule here. So we'll start off with the mule, and then we'll put cat, and then we'll put Earth. So for the mule, let's see if I can draw the mule. The mule has the following forces. This is the force of the Earth on the mule, and then it also has the force of the cat on the mule. And then for the cat, this is the force acting on the cat. This is the force of the mule on the cat. And let's ignore the weight of the mule and the weight of the cat, just so that we can make it simple. We already know how the weights pan out when we are analyzing Newton's third law, so we are also ignoring the weights. And then for the Earth, this is the force of the mule on the Earth. So let's bring it down here. So we have our mule again, we have cat, and we have Earth. So now applying second law, when we apply second law, we say the net force on the mule, or the net force, is equal to the mass times acceleration. So the forces on the mule are given. Those are the force of earth on the mule minus the force of the cat on the mule, and that will be equal to the mass of the mule times acceleration of the mule. And then we can say that acceleration of the mule is therefore equal to the force of the earth on the mule minus the force of cat on mule divided by mass of the mule. When we look at the cat, apply second law, and we say that the net force again is equal to MA. The net force on the cat is just the force of the mule on the cat. So the force of the mule on the cat is equal to the mass of the cat times acceleration of the cat. So acceleration of the cat is equal to the mass of the mule on the cat divided by the mass of the cat. And then for the earth, again apply second law, and again the net force is equal to mass times acceleration. So the force of the mule on the earth is the only external force present, and that's equal to the mass of the earth times acceleration of the earth. So from that we can say that acceleration of the earth is equal to the force of the mass on the earth, force of the mule on the earth divided by the mass of the earth. So we've completed analysis of this system of three objects: a mule, a cat, and the earth. Let's continue in this system. We can say that, so in this system where the mule and cat are connected, we can say that if the rope connecting them is massless, then the acceleration of the mule is equal to acceleration of the cat. So Newton's third law can be applied to various scenarios. I just described a few scenarios for you. It also applies to rocket motion. It will apply to the swimming of fish in the ocean and so on. So it applies to multiple scenarios, but I think we've covered most of the key scenarios. So let me finish up by saying that we have seen that in applying Newton's third law to systems of interacting objects, we can identify action and reaction pairs, and we can also analyze each object in the system individually by applying the second law. Let's look at an illustrative example of applying Newton's third law. Let's consider Atwoods Machine. So we have a fixed pulley, and on that pulley we hang a mass. Let's have this mass be M1, and then on the other side of the pulley we hang a mass M2. And let's consider that M1 rises upwards and M2 goes downwards. So we can apply Newton's second law to each mass. So consider each mass separately. So first of all, let's take the mass M1, and its weight is M1g, and the tension is T. And then for the second mass, we have M2g, and again the tension is T. We assume a frictionless pulley so that the tension is equal in both strings. By applying second law to each mass and tension, what we have is, for the mass going up, this is going up and this is going down. So we can say that for the first case, the net force is equal to the mass M1 times its acceleration A in the y direction, and we can say then that T minus M1g is equal to M1 A in the y direction. And then For a second object, net force is equal to M2A to A in the y direction, and for this situation, M2G minus T is equal to M2A in the y direction. We can solve for A in the y direction, and that gives us AY to be equal to M2 minus M1 divided by M2 plus M1 multiplied by G. So this gives us the acceleration of the masses, of the two masses in the Atwood machine. From that, we can calculate tension from one of the formulas. So we can say that T equals M1 G plus A in the y direction, and that's equal to 2 M1 M2 over M1 plus M2 multiplied by acceleration of gravity G. So you should work through these exercises yourself, solve the simultaneous equation yourself to get A subscript y, and then substitute A subscript y into one of those formulas up there to get a tension T. It doesn't matter which formula you use, you'll get the same result for tension T, since the tension is the same. So this is an important result to remember for the Atwood machine. So this is the end of chapter 7.